train 32 billion parameter LLM reasoning on just one GPU. H100 80 gigabytes of GPU is enough for this reinforcement learning LLM reasoning training. This is a paper by NVIDIA, MIT, Hong Kong University, and Tsinghua. I wrote an article that's easier to understand than the paper, and here you can see 1.7 times speed up, so 2000 tokens per second, while QLoRA and LoRA have around 1.5 thousand. It also uses up to 3 times less memory, so it can fit in a lot smaller GPUs. And there is no trade-off. In QLoRA, you make the model smaller but slower. But here you make the model smaller and faster. And this actually goes well with this NVIDIA's FP4 pre-training. So this is pre-training, and this is reinforcement learning that they just published, the reasoning training. And they use the same NVFP4 format of representing the numbers in 4 bits. Only the first 100 members that join my school get lifetime access for free, and then it's gonna become paid. So join right now. In our community, Become AI Researcher, we have exclusive courses on math, PyTorch, transformers, neural networks, and everything. Join for free right now as the base community member before I set the price. The problems this is solving: usually when you do reinforcement learning, reasoning training, you need to put multiple copies of the model onto GPU, at least 2 copies. One copy is the one that's being trained, and the other copy is frozen. So when you're updating the copy that's being trained, you don't want it to be too much different from the frozen copy. So they apply KL divergence loss to make this trained one not so different, but that's less important. What I'm trying to say is you need a lot of memory. And so this helps a lot. And this rollout phase is very slow, because this rollout phase is just when the LLM is generating tokens or answers. So you give it a task, you generate 16 different or 8 different answers, you pick the best one, and then teach the LLM to, with reinforcement learning, to generate that one. So, as you would imagine, this needs a lot of generation. So you're generating even like 4,000 tokens or even more of reasoning. So this quantization will actually make this faster, this process faster. And the problem with LoRA is it does reduce the number of trainable parameters you need to train, but it doesn't shrink the main model. So you still need to feed the whole model into memory. And QLoRA shrinks the main model. But due to this NF4 format, it actually makes now generating these tokens slower. So in QLoRA, you shrink the model, make it smaller, but also make it slower because it needs to do matrix multiplications in 16 bits, while the model is in 4 bits. So you need to convert from 4 bits to 16 bits all the time to do Matt Mulls. But in our new method, it does Matt Mulls in 4 bits, so there is no conversion. So this is a lot faster. And this image shows that. We got full LoRA, we got QLoRA, and we got our method. And then this bottom part I didn't explain yet. In this other blog post and this other video, I explained quantization. So when you have numbers represented in 16 bits or 8 bits, and you want to represent them in 4 bits, you can represent a lot less amount of numbers in just 4 bits. So I explained this scaling here, but basically you're gonna have to lose some precision because you can only represent these numbers, 0, 0.5, plus minus 1, and these numbers. So you need to shrink any range into this range. So you will have to round up, round down, so you will change numbers, you will lose some precision. But turns out this is actually good for reinforcement learning because this precision loss will make our output logits a bit more random. Now it's not gonna be so confident into the next word. Next token will be a bit more random, which is good for reinforcement learning where we need to explore a lot of different possible answers. So it's already randomizing our exploration, so that's actually, we are lucky here, it's good. Actually, we will need to add even more noise because even more noise will help us even more explore different answers. So in the beginning of reinforcement learning reasoning training, you want to make answer exploration more random. So we will add more noise in the beginning, and later we will not add more noise. We will just have this noise from quantization. So that's going to be enough noise for later stages where we want the model to exploit its learned knowledge more to generate correct answers, as opposed to explore more. So to summarize, in the beginning of reinforcement learning training, we add even more noise on top of this quantization noise, and then we reduce exponentially the amount of added noise. And then at the end, we just use this smaller quantization noise at the end of training, and model will learn very well with this. Here they just show that these up here quantized FP4 4-bit methods have more randomness or entropy compared to this gray float 16 LoRA, so 16-bit LoRA. And when you see this R32, that's just LoRA rank 32. So higher rank means more parameters for LoRA to adjust, so longer training and more accurate training. 32 is a good balance. Here we are using GRPO and Dapo reinforcement learning algorithms, reasoning algorithms, and we are comparing NV-FP4, our new method, with 16-bit LoRA, which is going to be slower, and full, no LoRA, but full pre-training, not just low rank, not just a part of parameters, but all of the parameters. And we can see that our method is almost performing same as the full parameter pre-training and it's reinforcement learning post-training. And it's performing better and learning faster than this 16-bit LoRA. So even though we are doing training a lot faster than training the whole full parameters, it's actually performing in the same amount of steps, even though our steps are a lot faster with our method. It's even outperforming the other famous 4-bit data type, which is this MXFP4. If I'm not mistaken, this is invented by OpenAI. Maybe I'm wrong. But you see that our method NVFP4 is learning faster at this point here. So it reaches this high reward faster. Now this is a bit weird because as I understand from the paper, they did all of this on H100 GPUs, but they don't support native FP4 Matt Mulls. So I don't know if they simulated it with this Marlin kernel or something, but this is probably made for Blackwell GPUs, the newest ones, that actually support FP4 Matt Mulls. So on Blackwells, this will run a lot faster. And that's why they figured out the LLM pre-training on Blackwells as well, one of the previous videos that I mentioned. But even if you cannot do Matt Mulls on H100, you can still have this model in 4 bits in memory and send it around, move it around in 4 bits, which will take a lot less memory and be a lot faster. And this is the adaptive quantization noise that I was talking about before. So even though this quantization adds a bit of noise to create tokens, to make tokens a bit more random, add a bit more exploration, we need to add even more noise in the beginning of the reasoning training to make it explore even more. So this is that noise, they made it exponentially decay. So in the beginning, there is a lot of noise, but later you see in the beginning this red line, a lot, but later it actually decays exponentially and then just a little bit of noise later. And this is on top of the already present quantization noise that's always the same and they don't touch that. And to add this noise more efficiently, they use a trick. So they merge this noise addition into this root mean square normalization layer. So I explained here the process in more details, but you see here the noise is added in RMS for both self-attention and for feed forward. And this here, up-down gate, seems like Swiglu. I just made a video a few days ago about Swiglu. You can watch that to learn more about the latest ways of coding transformers and large language models. And here we can see the full reasoning training. This seems to be happening in the fewest amount of steps. and then our method that's happening in more steps. However, these steps, as I'm understanding, are a lot faster. So maybe this red line will actually in reality happen even before, in less amount of time, because these steps are faster. And here LoRA doesn't converge at all for this amount of training. Maybe it will converge later, I'm not sure. And so they show that here as well on these two 7B, 14B models. And these are ablations with and without our added noise. So here with the added noise, it actually does learn a bit faster. So this red line is a bit before, a bit faster. And here as well. And it becomes even higher, so even more reward, so even smarter here. On this image, you can see how much faster our method is than LoRA. LoRA needs a lot more steps. And if this is 16, which is this is 16-bit LoRA, then per step is also a lot slower than 4-bit this method. That's it for this video. We already have 9 members. Until 100 members, my school is free to become AI researcher, and then it's gonna become paid, so join right now.